Alright, I got nothing on that one. Anyways, Iron's Physics Lesson 3.3. This is Newton's second law. We've already talked about this, so this is going to be a short section. But basically what we have is Newton's first law tells us when an object has net force at 0, and Newton's second law tells us when it's not 0. And that relates back to force equals mass times acceleration. Acceleration is measured in meters per second squared, force is measured in newtons, and mass is measured in kilograms. Sweet! So this brings us back to inertia, where we talk about what inertia's definition is in physics. So in physics, it relates highly to mass. A lot of times it's used interchangeably with the word mass, but it's an object's resistance to change motion. So the more mass, the more inertia, the more resistance it is to change. It's hard to stop a car from rolling versus a baseball from rolling, depending on their velocity or momentum. Alright, so Newton's second law basically states the harder you push something, the more it'll accelerate. And when you push something, the more mass it has, the less it will accelerate, kind of like the bowling ball. Alright, here we have it related to acceleration that allows us to see that acceleration is directly proportional to its net force and inversely proportional to its mass. So, in other words, force goes up, acceleration goes up. Mass goes up, acceleration goes down, and vice versa. Alright, so let's picture this. We have a 40 kilogram hockey goal. It's at rest. It's sitting on a frictionless or near frictionless hockey rink. And then I'm going to go through a couple of things that are happening in it. So Roy's going to push the goal. He's going to push it forward with 80 newtons for 6 seconds. So our force equals 80 newtons. Our mass equals 40 kilograms. So acceleration-wise, we don't know. So force equals mass times acceleration, that's the time sign, and we know our force, and that's 80 newtons. So our acceleration ends up being 2 meters per second squared. Alright, so if we're accelerating in this, that means that our velocity is going to change by 2 meters per second every single second that it goes. So time, velocity. So at 1 second, it's at 2. 2 seconds, 4, 3 seconds, 6, 4 seconds, 8. You catch the pattern here. The other way you can do this is acceleration equals velocity final minus velocity initial over time. And in this case, 2 equals Vf minus 0 at rest times 6. So the goal is moving at a velocity of 12 meters per second. Right, it's hustling down the rink. Now, Roy, let's go. Well, it's frictionless, so there's nothing to stop it. So even though a free body diagram of it would look like this: force of gravity, force of normal, force of gravity, and they're balanced, it's still moving at a constant velocity. So velocity is constant at that 12 meters per second. And it's going to remain that for the whole 4 seconds. It's not going to change. There's nothing to slow it down. There's nothing to speed it up. There's no acceleration. So we have a constant velocity. Alright, but now, oh, good old Sally. Sally is going to push backwards with a force of 120 newtons. Oh no! But she only does it for 2 seconds. So now we have a force of 120 newtons. Our mass is still 40 kilograms. So we need to figure out our acceleration. Our acceleration is negative 3 meters per second squared. Alright, so going back to our acceleration formula, negative 3 equals velocity final minus 12. Remember, it was going 12 meters per second when we left it, and our time is 2. So the velocity is still positive 6 meters per second. So it's still moving forward, only now it's moving a little bit slower, right? Velocity is decreased a little bit. Oops. Alright, so now, same hockey rink. Sally's still pushing with a negative 120 newtons. But now, Roy's going to push with a positive 120 newtons. He never really got along with Sally. And that's really bad, 120. I apologize. Yeah, not much better, but we'll live with it. So what's going to happen? Well, these two cancel out, so we have a net force of 0 newtons. So that means we're moving at constant velocity, which is still 6 meters per second. Right? We weren't able to change it all. Alright, but now Sally's going to increase her force to 140 newtons. Roy's still pushing. Those are supposed to be a little bit shorter. Do it like that. 120 newtons. So now we have a net force of negative 20 newtons. Equals our mass, which is 40 kilograms, times our acceleration. So our acceleration is negative 0.5. So now our velocity, every second that we have this situation, is going to decrease by 0.5 meters per second. So after 1 second, it'll be negative 5.5, then negative 5, or not negative, positive 5, then 4.5, then 4, then all the way down to 0, and then past that. So what we can do, I'll change colors here, is we can take this negative 0.5 equals velocity final minus our 6 and then times time. So we get negative 5 equals velocity final minus 6. Still moving forward, but not for much longer. Alright, well, that was 3.2. I forgot, I got one other thing I want to show you. So Newton's laws are usually written as force equals mass times acceleration. So what we could always do is just take the mass and times it by the acceleration, just like we did in the other problem. So what force would you need? 18 newtons, right? Mass times acceleration. Alright, yay! Fun times. Alright, talk to you later. Goodbye.